Hello, assembler class students. This video is to help you prepare for the standard deviation homework, where you program in the language of your choice. But the idea is to learn a little bit about the limits of floating point numbers. And we'll start by, in this video, taking a quick overview without going into most of the details of floating point representation. And as you would expect, they're going to be binary numbers. And chapter 6 in the Carter book explains this in some detail. And as you know, floating point numbers are what? Fractions, right? So we're going to have binary fractions with a binary point or a decimal point, whatever you want to call it, and sometimes a mathematician calls it a radix point, and we have digits afterwards. So if we have a number in decimal like 0.123, that's the 1 over 10 place, the 10 to the minus 1 place. That's 2 times 1/100th, 10 to the minus 2, and plus 3 times 1,000th, 10 to the minus 3. It'll be the same with binary numbers. This is the 1/2 place, 1 over 2, and then 1 over 4, and then 1 over 8, 1 over 2 to the 3. So we add those up. We have a half plus no quarters plus an eighth makes 5/8, and that's 5/8. And we could have digits to the left of the radix point, no problem. That's a binary 6, and then no halves, and then a quarter and an eighth. So that's going to be 6 3/8, like that. Okay. So that's the basic notion of how we represent fractional numbers with binary points or decimal points in on a computer, in binary. And I will just touch briefly on what this looks like in memory, which I think will be right here. So this is a 4-byte D word in x86 architecture terminology. It's going to have 23 bits of significant bits. That's called F over here, is the fractional part. And because we don't really, 0 is going to be represented in a special way. So the fractional part can never actually be 0. So we're going to adopt the convention that there's always one digit to the left of the binary point. I mean, you've seen that in scientific notation. Something point blah 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 times 10 to the something, right? So that something, if it's not 0, has got to be 1. So there's a 1 to the left of these 23 fractional bits. There's 23 fractional bits over here, and a 1 to the left of it, 1 point blob. We have 8 bits of exponent. So roughly speaking, the exponents can be plus or minus 127, and anything in between. Okay, there's a way of sort of stretching things a little bit. The representation isn't 2's complement plus or minus numbers. It's something called excess 127. So we take this as a positive number and subtract 127 from it. That gets us our exponent. But there's ways of stretching the numbers to somewhat more negative exponents if we lose some precision. But that's not something we really need to go into. And then we'll get a sign bit. So fundamentally, we have a 24-bit fraction starting with 1 point something times 2 to the some number, and then plus or minus in the front. And that's the basic single precision floating point. So in Java or C or C++, if you have a number declared float, this is what it is. If you have a number which is declared a double, it's bigger. It's 8 bytes long. It's 8 bytes long, and it has 52 bits or 53 bits of precision, and 10 bits of or 11 bits of exponent, which means you can go to plus or minus 1023, like that. But and in Python, they're all doubles. For purposes of this assignment, we're thinking only about the singles, the things that are called floats. So without further ado, I'm going to go to a note over here. And the first thing we're going to notice about binary numbers, and Carter covers this, is that you don't get as many numbers represented exactly. Like in decimal, 0.2 is an exact number. 1/5 is an exact number. And if I multiply 1/5 by 5, I get 1. Here's what happens in binary. We're going to do long division. This is 1 divided by 101. So here's your long division from 4th grade. So here's 1.00000 divided by 101. And I started it for you because the first place we can put the 101 is over here, because it's the 1 and 4 zeros minus 101. So there's a 1 up there, right? And we'll subtract. And I can subtract by, 0 minus 1 is 1 with borrowing the 1s like that. And that's easy to do, but even easier is to look at that part and say that's 8, that's 5, so this is going to be 3. So 1000 minus 101 is 311. So then what? I have another 0 up here, right? And now I can put 101 in there again, which allows me to put a 1 up here, right? Remember your long division. So what? So I can subtract the 1 and borrow. Okay, I get a 1 over there. And now I've borrowed, so there's a 0 over here. Excuse me. And a 0, right? So basically I got 1 out. Or you could say this is 6 minus 5 is 1. Alright. Alright, now what? So now I have to put another 0 there. Another 0 there. And another 0 there. And now I can actually put 101 in here, right? Alright, so we're back where we started. Here we have, 8 minus 5 again, right? So we're back down to 3. Alright, and now that 0 goes down, and that means I can put another 1 here. And on the next line we're going to get 101, right? And, down here is going to be 1. So I'm repeating, right? You can see I'm repeating myself now. Starting from here is where I'm repeating, right? So we repeated the 1, 1. So what this is going to look like is 0011, 0011, 00, because here I am, 000, okay? 0011, 0011, like that, okay? So 1/5 in binary is an infinite repeating fraction, which means that if I take like 1/5 and I'm going to only represent it to so many sig figs, even if it's 24 sig figs, it's only so many. If I take 1/5 and multiply it by 5, I might not get 1. I might get 1 if I'm rounding, but you see what's going to happen, that a lot of numbers which are exact are going to be really darn close, but not exact. That phenomenon of taking 1/3, multiplying it by 3 and getting 0.99999, that's going to happen a lot. Okay, So that's the first phenomenon that we need to notice that shows us that these floating point numbers in computers are going to be just a little bit different and slightly more dangerous than the decimal numbers that we're accustomed to. Going down a little bit, let's think a little bit about computing using fixed numbers of significant figures. So single precision floats are 24 sig figs. That's 1 point blah 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 with 23 times 2 to the power of something. All right, double precisions. I'm sorry, they have 53 bits. That's my mistake. Okay, and in Java, as I mentioned, the shorter ones are called floats and the longer ones are called doubles, the same as in C and C++. So let's remember what arithmetic looks like using scientific notation. So if I have a number like 12.3, I write it in scientific notation like that, or it could be 0.123 times e to 10 to the 2. Either it doesn't make much difference. If I have a number like 0.456, that's how I write it. If I want to add these, I got to adjust the exponents to line them up, right? So that's 1.23 times 10 to the 1 plus 0.04 times 10 to the 1. Okay, I've got to adjust that to be 10 to the 1. So what the computer does usually, and what you frequently do, is you'll add one more digit in there, which we call a guard digit, just temporarily. So 0.0456 is going to be rounded in that guard digit to plus 0.46. So using that extra sig fig, I add everything up, and then I round, and that's where my answer is. So that's what happens when we are adding using 3 sig figs. And the same thing is going to happen in binary. And the lesson is that I'm going to end up losing stuff off the end, right? Basically, it treated the 0.456 as 0.5 because this 4.56 was down here in the last significant figure of the top number. So basically, I added 1.23 plus 0.5 and got 1.28, and I lost some digits from the intermediate part of the computation. Okay, so that's what's going on with floating point numbers, and those are the two ways in which they are, can be dangerous. They're also dangerous if you, exceed your exponents, but with exponents like 120 something or 1,000, we're not going to worry about that particularly. That usually won't bite you by accident. And I will post this up to Blackboard, but let's end this video.